May 4, 1945. Chofu Airfield, Tokyo, Japan. Captain Yoshitaka Kudo climbs into the cockpit of Republic P-47 Thunderbolt, serial number 42-25618. The aircraft was captured 3 months earlier in the Philippines, after an emergency landing left it intact in Japanese hands. Kudo has flown Zeros, Oscars, even captured American Wildcats during evaluation testing. He understands enemy aircraft, but nothing has prepared him for what he's about to experience. The Pratt and Whitney R2800 double Wasp engine sits in front of him like a monument to industrial excess. 18 cylinders, 2,800 horsepower. The engine alone weighs more than an entire Mitsubishi A6M0 fighter. Ground Crew Chief Technical Sergeant Takeshi Nakamura completes the pre-flight check. His report, preserved in Japanese Air Technical Arsenal records, notes fuel load at 370 gallons, enough for exactly one test flight before the captured aircraft must be grounded. Japan has no aviation fuel to waste. Kudo starts the engine. The sound is unlike anything he's heard before, not the high-pitched whine of Japanese radial engines, but a deep, mechanical thunder that vibrates through the airframe. The propeller, 13 feet in diameter, begins to turn. The entire aircraft strains against its brakes like a chained beast. At 09:15 hours, Kudo releases the brakes. The Thunderbolt accelerates. 200 feet. 300 feet. The tail lifts. At 400 feet, the massive fighter becomes airborne. Climb rate, 3,000 feet per minute. A Zero takes twice as long to reach the same altitude. Kudo levels off at 15,000 feet and opens the throttle. The acceleration presses him back into his seat with force he's never experienced in a Japanese fighter. Airspeed indicator climbs. 300 miles per hour, 350, 400, 428. The Thunderbolt is still accelerating when Kudo closes the throttle, not because the aircraft has reached its limit, but because he has reached his. His post-flight report, translated from Japanese Technical Air Arsenal document T-47-05, states, American fighter demonstrates performance characteristics that cannot be matched by any aircraft in Japanese inventory. Speed, climb rate, dive performance, and structural strength all exceed Imperial Japanese Army Air Force capabilities. Most concerning, this performance appears to be standard for American fighter production, not experimental. If this represents typical American fighter capability, we are fighting an air war we cannot win. By May 1945, Japanese military leadership knew they were losing the war. What they didn't understand was exactly how far behind they had fallen in aviation technology. Kudo's test flight report provided the answer, and it was devastating. If you're enjoying this deep dive into the story, hit the subscribe button, and let us know in the comments from where in the world you are watching from today. The story begins not in the skies over Tokyo, but in the factories of Farmingdale, New York, where Republic Aviation Corporation built fighters that would redefine aerial warfare. In 1941, as Japan prepared for war against America, the United States Army Air Corps issued a requirement for a new fighter aircraft. The specification demanded 8 50-caliber machine guns, armor protection for the pilot, self-sealing fuel tanks, and performance superior to any existing fighter. Most importantly, it required an aircraft that could escort bombers deep into enemy territory and fight its way home. Republic Aviation's chief designer, Alexander Kartveli, submitted a proposal that shocked Army evaluators. His fighter would weigh 13,000 pounds empty, nearly triple the weight of contemporary fighters. It would be powered by the most powerful aircraft engine in production, the Pratt and Whitney R2800, generating 2,000 horsepower. It would be armored like a tank and armed like a destroyer. Army procurement officers initially rejected the design as too heavy, too complex, too expensive. Kartveli's response, documented in Republic's project files dated June 15, 1941. You asked for a fighter that can protect bombers and survive combat. I designed exactly that. Light fighters die, heavy fighters come home. The Army reconsidered. In September 1941, 3 months before Pearl Harbor, Republic received a contract for 171 aircraft designated XP-47B. First flight occurred on May 6, 1942. The test pilot, Lowry Brabham, reported the aircraft handled like flying a freight train with wings. The P-47 Thunderbolt was the largest, heaviest, most powerful single-seat fighter aircraft ever built at that time. Empty weight, £10,300. Maximum takeoff weight, 17,500 pounds, heavier than many twin-engine bombers. Wingspan, 40.9 feet. Length, 36.1 feet. But the statistics that mattered most centered on the engine. The Pratt and Whitney R2800 double Wasp was a masterpiece of American engineering. 18 cylinders arranged in 2 rows of 9, displacement, 2,804 cubic inches. Maximum horsepower, 2,800 at takeoff, reducing to 2,300 for continuous operation. The engine consumed 130 gallons of fuel per hour at maximum power. It required 56 spark plugs, 2 magnetos, and a 2-stage supercharger that weighed 500 pounds by itself. The supercharger was critical, maintaining engine power at high altitude where thin air would normally strangle performance. At 25,000 feet, where most Japanese fighters struggled to operate effectively, the P-47 supercharger compressed incoming air to sea-level density. The R2800 continued generating over 2,000 horsepower at altitudes where Japanese engines produced barely 1,000. This high-altitude performance revolutionized fighter tactics. P-47 pilots could climb above Japanese fighters, dive to attack with speed advantage, then climb away before the enemy could respond. The Japanese called this tactic boom and zoom. American pilots called it not dying. But power came with complexity. The R2800 required precise maintenance, oil changes every 50 hours, spark plug inspection every 25 hours, supercharger bearing checks every 100 hours. Valve adjustments demanded specialized tools and trained mechanics. A single R2800 engine required 43 hours of maintenance labor per 100 flight hours. Japanese engines, by contrast, were designed for simplicity. The Nakajima Sakai engine powering the Zero required 15 hours of maintenance per 100 flight hours. Fewer parts, simpler construction, easier maintenance. But the trade-off was power. The Sakai generated 1,130 horsepower. The R2800 generated more than double that output. This power difference created performance gaps that tactics couldn't overcome. Maximum speed of the Mitsubishi A6M50, 351 miles per hour. Maximum speed of the P-47D Thunderbolt, 433 miles per hour. Speed advantage, 23%. Maximum dive speed of 0, 410 miles per hour before structural failure. Maximum dive speed of P-47, 550 miles per hour with safety margin. Dive advantage, 34%. Service ceiling of 0, 36,000 feet. Service ceiling of P-47, 43,000 feet. Altitude advantage, 19%. These percentages translated to life and death in combat. A Zero pilot who encountered a P-47 at altitude had 3 options: dive away and hope to escape, attempt to dogfight and exploit the Thunderbolt's poor maneuverability at low speed, or climb higher where the Zero's lighter wing loading provided advantage. All 3 options assumed the P-47 pilot made mistakes. Against competent P-47 pilots who understood their aircraft's strengths, Japanese fighters had no good options. American pilots could dictate engagement terms, attacking when advantageous and disengaging when threatened. The Japanese called fighting P-47 seconds chasing thunder, an exercise in futility. Production of the P-47 began in earnest in 1943. Republic's Farmingdale plant employed 42,000 workers operating in 3 shifts, 24 hours per day. Peak production, 33 aircraft per day. Annual output, 12,000 aircraft, more than Japan's entire fighter production for the same period. The scale of American production shocked Japanese intelligence analysts. A single American factory produced more fighters than Japan's entire aviation industry. And Republic was just one of several American manufacturers. Consolidated, North American, Lockheed, Grumman, each operated multiple factories producing thousands of aircraft monthly. Japanese pilot training programs couldn't keep pace. Training a competent fighter pilot required 6 months minimum, longer for advanced combat techniques. Training an aircraft mechanic required 4 months. Japan was losing pilots and mechanics faster than schools could replace them. Meanwhile, America graduated thousands of pilots and tens of thousands of mechanics monthly from dozens of training facilities. By 1944, the imbalance had become catastrophic. Japanese factories produced approximately 28,000 aircraft during the entire war. American factories produced nearly 300,000 aircraft during the same period. Ratio: 10-1 in America's favor. More concerning for Japan, American aircraft grew progressively better throughout the war, while Japanese designs stagnated. The P-47D model that Captain Kudo would eventually fly represented the culmination of continuous improvement. Compared to the original P-47B, the D model featured water injection for emergency power boost, improved supercharger for better high-altitude performance, and increased fuel capacity for longer range. The water injection system deserves special attention. By injecting a water-methanol mixture into the engine during takeoff or emergency combat, pilots could temporarily boost power output to 2,550 horsepower, a 10% increase. This boost lasted only 5 minutes before depleting the 15-gallon water-methanol tank, but 5 minutes of extra power often meant the difference between escape and death. Japanese engineers understood water injection theory. They lacked the industrial capacity to implement it. Water injection required precise fuel metering systems, corrosion-resistant plumbing, and high-quality methanol. Japan's strained chemical industry couldn't produce sufficient methanol for widespread military use. The feature that gave American fighters emergency power remained unavailable to Japanese pilots who needed it most. Armament told a similar story of industrial disparity. The P-47D carried 8 M2 Browning 50 caliber machine guns, 4 in each wing. Total ammunition, 3,400 rounds. Rate of fire, 800 rounds per minute per gun. Combined firepower, 6,400 rounds per minute. Each 50 caliber bullet weighed approximately 1.7 ounces. At maximum rate of fire, the P-47's guns hurled nearly 90 pounds of lead per minute toward targets. The recoil from firing all 8 guns simultaneously reduced the aircraft's speed by approximately 15 miles per hour. Japanese fighters typically carried 2 20mm cannons and 2 7.7mm machine guns. Total weight of fire, approximately 40 pounds per minute, less than half the P-47's output. Worse, Japanese cannons had low muzzle velocity, making long-range shooting difficult. American 50 caliber guns maintained accuracy at 800 yards, double the effective range of Japanese weapons. But the P-47's most important feature wasn't its guns or engine, it was durability. Republic engineers designed the Thunderbolt to survive damage that would destroy lighter fighters. The aircraft could sustain hits from 20mm cannon shells and continue flying. Armor plate protected the pilot from behind and below. Self-sealing fuel tanks prevented fire when punctured by bullets. Combat reports from the Pacific Theater documented this survivability. 5th Air Force records from 1944 show P-47 seconds returning to base with hundreds of bullet holes, damaged control surfaces, and partial engine failures. The aircraft kept flying. Pilots kept surviving. Japanese fighters, optimized for weight reduction to maximize maneuverability, lacked this damage tolerance. A single well-placed burst could sever control cables, rupture fuel tanks, or kill the pilot. Japanese aviation philosophy prioritized offensive capability over defensive protection, assuming skilled pilots would avoid getting hit. This worked against poorly trained opponents. Against American pilots with superior aircraft, it was suicide. The captured P-47 that Captain Kudo would eventually fly came into Japanese hands through a combination of mechanical failure and bad luck. On January 27, 1945, First Lieutenant James Morrison of the 58th Fighter Group encountered engine trouble during a bomber escort mission over Luzon, Philippines. Morrison's post-rescue debriefing, declassified in 1973, describes the failure. I was at 18,000 feet when I heard unusual vibration from the engine. Oil pressure began fluctuating. Temperature climbed above normal operating range. I recognized the symptoms of impending bearing failure and began descending toward Allied territory. The engine seized at 4,000 feet, approximately 12 miles behind Japanese lines. Morrison attempted a forced landing in a rice paddy. The Thunderbolt touched down at 90 miles per hour, far faster than ideal but survivable. The aircraft slid 700 feet before stopping, structurally intact but with a destroyed engine. Morrison evacuated immediately. knowing Japanese troops would investigate the crash. He survived 3 days in the jungle before Filipino guerrillas found him and arranged extraction via submarine. His aircraft wasn't as fortunate. Japanese troops secured the crash site within hours and transported the P-47 to Manila for evaluation. From there, it travelled by ship to Japan, arriving at Chofu Airfield in March 1945. The Japanese air technical arsenal, responsible for evaluating captured enemy equipment, faced immediate challenges. The P-47 required high-octane aviation fuel, 130 octane minimum for optimal performance. Japan's refineries produced primarily 87 octane fuel, barely adequate for Japanese aircraft and completely unsuitable for the R-2800 engine. Technical arsenal engineers cobbled together sufficient 100 octane fuel for limited testing by blending their highest-grade aviation fuel with additives. Total available fuel, approximately 450 gallons, enough for perhaps 3 test flights before the experiment ended. Repairing Morrison's damaged P-47 presented additional problems. The seized engine was beyond salvage. Fortunately, or unfortunately from the Japanese perspective, the technical arsenal had one spare R-2800 engine. This engine had been salvaged from another P-47 that crashed in China in 1944 and had been laboriously transported to Japan for study. Installing the replacement engine required American tools the Japanese didn't have, American technical manuals written in English that required translation, and American mechanical expertise that Japanese technicians had to develop through trial and error. The installation took 3 weeks. A trained American ground crew could have completed the same task in 18 hours. On April 16, 1945, ground testing began. The Japanese technicians managed to start the R-2800, a significant achievement given the engine's complexity. But running an engine on a test stand differed from operating it in flight. The technical arsenal needed a pilot willing to fly a barely understood foreign aircraft with questionable maintenance using improvised fuel. Captain Yoshitaka Kudo volunteered. At 31 years old, Kudo had accumulated over 2,000 flight hours in Japanese fighters, plus evaluation time in several captured American aircraft. His experience with captured P-51 Mustangs and P-38 Lightnings made him the most qualified pilot available. His pre-flight briefing, conducted on May 3rd, covered basic P-47 systems. American technical manuals provided specifications, but practical knowledge gaps remained enormous. Kudo would be teaching himself to fly the Thunderbolt with minimal ground instruction and no dual-control trainer for practice. The briefing notes, preserved in Japanese archives, reveal the technical arsenal's concerns. Pilot is reminded that American aircraft control responses differ from Japanese practice. Throttle advances forward for power increase, opposite of Japanese standard. Landing gear retracts upward into wings, not rearward into fuselage. Flap operation is electric, not hydraulic. Most critically, aircraft weight is triple that of Zero fighter. Landing speed will be approximately 120 miles per hour, requiring long runway and careful approach management. May 4th, 1945. 0900 hours. Captain Kudo completes his pre-flight inspection of the captured Thunderbolt. The aircraft dwarfs the Zeros parked nearby. Standing next to the P-47, Kudo barely reaches the bottom of the cockpit. He climbs the wing route, enters the cockpit, and begins the starting sequence. The cockpit layout confuses him immediately. American instrumentation uses English labels and imperial measurements. Airspeed in miles per hour, not kilometers. Altitude in feet, not meters. Fuel quantity in gallons, not liters. Kudo has studied translated manuals, but reading about instruments differs from interpreting them under flight conditions. The engine start procedure requires 14 steps. Kudo follows his checklist methodically. Fuel selector to main tank, mixture to idle cutoff, propeller control full forward, throttle 1 inch forward, battery on, fuel pumps on, wait for fuel pressure stabilization, mixture to auto-rich, ignition switch to both magnetos. Engage starter. The R-2800 coughs, backfires, and catches. 18 cylinders fire in sequence, creating a sound that physically shakes the aircraft. Exhaust flames shoot 4 feet from the stub exhausts, mounted on each side of the cowling. The propeller accelerates to 1,000 revolutions per minute. Oil pressure climbs into the green arc. Cylinder head temperature rises steadily. Kudo advances the throttle slightly. The engine responds instantly, surging to 1500 RPM with a sound like continuous thunder. The entire airframe vibrates. Control surfaces flutter in the propeller wash. Ground crew members standing behind the aircraft lean into the prop blast to avoid being knocked over. At 09:13 hours, Kudo signals for wheel chocks to be removed. He releases the brakes and adds power. The Thunderbolt begins rolling. Kudo's first surprise. The aircraft requires significant forward pressure on the control stick to keep the tail on the ground. The massive engine and propeller create tremendous torque trying to flip the nose downward during taxi. The second surprise comes when Kudo tests the brakes. The P-47's brakes are far more powerful than anything on Japanese fighters. Light pressure brings the 13,000-pound aircraft to a rapid stop. Too much pressure would blow the tires or damage the landing gear. Kudo makes a note. American brakes require gentle touch. He taxis to the end of Chofu's main runway, 2,400 meters of concrete. Chofu was built to handle Japanese bombers, so length isn't a concern. Width and surface condition are adequate. Kudo runs through the pre-takeoff checklist. Flaps set to 15 degrees. Trim tabs neutral. Propeller pitch full forward. Mixture auto-rich. Fuel on main tank. Canopy closed and locked. At 09:15 hours, Kudo advances the throttle to full power. The response is immediate and overwhelming. The R2800 leaps from idle to maximum output in 3 seconds. The acceleration pins Kudo against his seat. The propeller reaches 2,700 RPM. Manifold pressure climbs to 52 inches. 2,800 horsepower tries to drag the Thunderbolt into the sky. The tail lifts at 40 miles per hour. Kudo eases back pressure on the stick. The aircraft tracks straight down the runway despite the tremendous torque. At 85 miles per hour, Kudo pulls back gently. The Thunderbolt rotates. At 93 miles per hour, the aircraft breaks ground. 470 feet of runway consumed. A Zero requires less than 300 feet for takeoff, but the Zero weighs less than half what the P-47 weighs. Kudo retracts the landing gear. The hydraulic system whines as wheels fold upward into wing cavities. The aircraft accelerates. 120 miles per hour, 150, 200. Kudo has used barely 1/3 power, and already the Thunderbolt flies faster than a Zero at maximum speed. He begins a climbing turn. The P-47 responds sluggishly at low speed, exactly as briefed. The aircraft wants to fly fast and doesn't appreciate being asked to maneuver slowly. Kudo adds more power. Climb rate increases to 2,000 feet per minute. At this rate, reaching 20,000 feet will take 10 minutes. A Zero would require 15 minutes for the same climb. At 5,000 feet, Kudo levels off and begins exploring the flight envelope. First test. Roll rate. He banks left, then right, holding moderate back pressure on the stick. The Thunderbolt rolls slowly but powerfully. Ailerons are heavy, requiring significant stick force, but they work effectively. The aircraft responds like it weighs over 6 tons, because it does. Second test. Pitch response. Kudo pulls back on the stick. The nose rises smoothly. He pushes forward. The nose drops. Elevator control feels normal, neither too heavy nor too light. The aircraft is stable, predictable, exactly what a bomber escort needs. Third test. Yaw control. Kudo applies rudder pressure. The nose yaws left, then right. Rudder forces are surprisingly light for such a large aircraft. He makes a note. The oversized rudder provides excellent directional control. At 10,000 feet, Kudo attempts a Japanese-style turning engagement, the kind of dogfight Zero pilots train for constantly. He pulls hard into a left turn, loading the aircraft to 4 Gs. The Thunderbolt turns, but slowly. Turn radius is enormous compared to a Zero. Turn rate is ponderous. If this were actual combat, a Zero would easily outturn the P-47 and achieve firing position. But Kudo immediately recognizes the flaw in this analysis. The P-47 isn't designed to dogfight. It's designed to dictate engagement terms. He rolls level, advances throttle to maximum, and pushes the stick forward into a dive. The acceleration is extraordinary. The airspeed indicator winds up like a clock spring. 250 miles per hour, 300, 350, 400. The aircraft is still accelerating smoothly with no vibration, no buffeting, no indication of structural stress. Kudo glances at the placard on the instrument panel showing maximum dive speed, 550 miles per hour. He's nowhere near the limit. At 428 miles per hour, Kudo pulls out of the dive. The G-forces press him into his seat. He estimates 4 Gs, possibly 5. The airframe handles the stress without complaint. No creaking, no flexing, no signs of distress. American structural engineering has created an aircraft that can absorb forces that would rip a Zero's wings off. Climbing back to 15,000 feet, Kudo considers the tactical implications. A Zero pilot who sees a P-47 at altitude cannot catch it. If the P-47 dives, the Zero cannot follow without risking structural failure. If the Zero turns to dogfight, the P-47 can simply extend away using superior speed. The only Japanese advantage, maneuverability, becomes irrelevant when the American pilot refuses to engage in turning combat. At 15,000 feet, Kudo tests the aircraft's high-altitude performance. He advances throttle to maximum continuous power and begins climbing. The R-2800's two-stage supercharger engages automatically, compressing thin air to maintain manifold pressure. Climb rate remains above 2,000 feet per minute, even at altitude where Japanese fighters struggle. 20,000 feet, 25,000 feet, the Thunderbolt continues climbing strongly. At 30,000 feet, Kudo levels off. He checks engine instruments. Manifold pressure, 46 inches. RPM, 2,500. Cylinder head temperature, 240 degrees Celsius, normal operating range. Oil pressure, 75 pounds per square inch, normal. 2,500 for square inch, normal. The R-2800 is operating at full power at an altitude where Japanese engines would be gasping. Kudo advances throttle and accelerates to maximum speed at 30,000 feet, 405 miles per hour. At this altitude, this speed, no Japanese fighter can touch him. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Kudo descends to 15,000 feet and begins combat maneuver testing. First, the high-speed yo-yo, an American tactic where the fighter dives to build speed, then zooms back to altitude to attack. Kudo pushes into a dive, accelerates to 450 miles per hour, then pulls into a vertical climb. The Thunderbolt rockets upward, 5,000 feet, 10,000 feet, 15,000 feet vertical gain before speed bleeds off. A Zero attempting the same maneuver would gain perhaps 3,000 feet before stalling. The power-to-weight ratio makes the difference. The P-47 has enough excess power to convert speed into altitude rapidly. Japanese fighters lack this capability. Second maneuver. The defensive split S. Kudo rolls inverted and pulls through into a dive, a standard escape maneuver. The Thunderbolt handles the reversal easily, accelerating through the dive to 400 miles per hour in seconds. Any pursuer would need equal or better dive performance to follow. No Japanese fighter qualifies. Third maneuver. High G turns at high speed. Kudo attempts a maximum rate turn at 350 miles per hour. The aircraft turns tightly, loading to 6 Gs. Kudo feels the G-forces pressing him into his seat, greying his vision slightly. The airframe handles it without stress. American fighters are built to sustain G-forces that would disable Japanese pilots who lack G-suits. After 45 minutes of flight testing, Kudo begins his approach to Chofu. The return pattern requires careful planning. The P-47 lands fast, much faster than Japanese fighters. Approach speed at landing weight, 120 miles per hour. Touchdown speed, 105 miles per hour. These speeds exceed the maximum speed of many Japanese trainer aircraft. Kudo enters the landing pattern at 1,000 feet, reduces power, and extends landing gear. The hydraulics whine again as wheels lock down. Green indicator lights confirm gear extension. He extends full flaps, which creates significant drag and allows him to reduce speed to 125 miles per hour while maintaining controlled flight. The Thunderbolt handles nicely on approach despite its weight. The big wing provides plenty of lift even at slow speeds. Kudo crosses the runway threshold at 120 miles per hour, reduces power to idle, and begins the flare. The aircraft settles onto the runway at 108 miles per hour. Touchdown is firm but controlled. Kudo applies brakes gently. The powerful American brakes slow the massive fighter rapidly. Total landing roll, 850 feet, remarkably short for such a heavy aircraft. Kudo taxis clear of the runway and shuts down the engine at 10:35 hours. Total flight time, 1 hour, 20 minutes. Fuel consumed, 240 gallons, leaving 130 gallons in the tanks. Ground crew swarm the aircraft immediately. They check for damage, inspect tires, examine engine oil for metal particles indicating internal wear. The aircraft is in perfect condition. The engine ran flawlessly despite the improvised fuel mixture. Kudo's debriefing begins immediately. Technical Arsenal engineers question him about every aspect of the flight. His responses, recorded in Japanese Air Technical Arsenal document T-47-05, provide extraordinary insight into Japanese assessment of American aviation capability. On speed. Maximum speed at altitude exceeds 400 miles per hour, with power remaining available. American pilot who maintains altitude advantage cannot be caught by Japanese fighters. Dive speed approaches 500 miles per hour. No Japanese aircraft can follow P-47 through high-speed dive without structural failure. On-climb performance. Rate of climb exceeds 2,000 feet per minute, from sea level to 30,000 feet. Climb to combat altitude requires approximately half the time Japanese fighters need. American fighters can therefore dictate engagement altitude, always fighting from superior position. On high-altitude performance, engine maintains full power above 30,000 feet. Japanese fighters at same altitude operate at reduced power, creating performance disparity that favors American aircraft. High-altitude combat is impossible for Japanese fighters against this aircraft. On maneuverability, turn performance is inferior to Japanese fighters. Turn radius is large, turn rate is slow. However, this weakness is irrelevant because American pilots refuse to engage in turning combat. They use speed advantage to attack and escape before Japanese fighters can counter-maneuver. On durability, airframe construction is extremely heavy and strong. Aircraft can sustain battle damage that would destroy Japanese fighters. Pilot armor protection is comprehensive. American pilots who would die in Japanese aircraft survive in this machine. On armament, 850 caliber machine guns provide devastating firepower. American pilots can engage from longer range than Japanese weapons allow. Combined with speed advantage, this creates tactical situation where American aircraft can attack Japanese fighters while remaining outside effective range of Japanese guns. On maintenance, engine complexity is extreme. Japanese mechanics cannot maintain this aircraft without American tools, manuals, and training. The R-2800 engine represents industrial capability Japan does not possess. We can capture American aircraft but cannot operate them sustainably. The final paragraph of Kudo's report provides the strategic assessment that Japanese High Command didn't want to hear. This aircraft represents standard American fighter production, not experimental or specialized equipment. America is producing thousands of these aircraft monthly. Each one is superior to our best fighters in speed, altitude performance, and durability. Our maneuverability advantage is tactically irrelevant against pilots who refuse to dogfight. We are fighting an air war with inferior equipment and insufficient numbers. Unless we develop equivalent aircraft immediately, air superiority is impossible. Technical Arsenal Director Colonel Takeo Yasuda forwarded Kudo's report to Imperial Japanese Army Air Force Headquarters, with his own commentary dated May 8, 1945. Evaluation confirms American aviation technical superiority in all categories except maneuverability. Most critically, this superiority appears to be routine production standard, not limited to advanced models. American industrial capacity produces thousands of high-performance aircraft, while Japanese factories struggle to maintain current production levels. Recommendation: acknowledge air superiority is unattainable with current Japanese aircraft designs. The report reached Army headquarters on May 10th. By then, Germany had surrendered, ending the war in Europe and allowing America to redirect its full industrial might toward Japan. The strategic situation made Kudo's technical assessment even more devastating. Japanese aviation industry monthly production in May 1945. Approximately 1,000 aircraft of all types, many constructed from substitute materials because aluminum was scarce. American aviation industry, monthly production in May 1945. Approximately 9,000 aircraft of all types, all built from high-quality materials using standardized production methods. The P-47 alone accounted for approximately 700 aircraft per month from Republic's factories. Add production from other American manufacturers, Mustangs, Corsairs, Hellcats, Lightnings, and the disparity becomes overwhelming. Japan faced an enemy producing 9 times more aircraft, using superior designs with better engines. But numbers tell only part of the story. Quality mattered as much as quantity. The R-2800 engine that powered the P-47 represented industrial capability. Japan couldn't match. American factories produced over 125,000 R-2800 engines during the war. Each engine required precision machining, specialized metallurgy, and quality control standards Japanese industry couldn't maintain. The supercharger alone demonstrated the gap. A 2-stage supercharger requires precise turbine blade construction, bearing tolerances measured in thousandths of an inch, and heat-resistant materials that maintain properties under extreme stress. American factories built these components to exacting standards on production lines, employing tens of thousands of workers. Japanese factories attempted similar systems, but achieved only limited success with single-stage superchargers that provided inferior performance. Fuel quality created another insurmountable barrier. The R-2800 required minimum 100-octane fuel to operate safely. Higher octane fuel allowed higher manifold pressures, which generated more power. American refineries produced 130-octane fuel in sufficient quantities to supply the entire military. Some P-47 seconds used 150-octane fuel for emergency war power, generating over 2,600 horsepower temporarily. Japanese refineries struggled to produce 87-octane fuel. Attempts to create higher octane fuels through catalytic cracking and chemical additives achieved limited results. The best Japanese aviation fuel tested at 92 octane, barely adequate for Japanese engines and completely unsuitable for American engines designed for higher octane operation. This fuel disparity affected every aspect of aviation performance. Japanese engines couldn't generate power comparable to American engines even with similar displacement, because lower octane fuel limited compression ratios and manifold pressures. The Nakajima Homare engine, Japan's most powerful aircraft engine, displaced over 2,500 cubic inches, but generated only 1,900 horsepower. The R-2800, with similar displacement, generated 2,800 horsepower using superior fuel and better metallurgy. Pilot training revealed similar disparities. By 1945, American pilot training programs graduated approximately 4,000 pilots monthly from dozens of training facilities. Training included 250 hours minimum flight time before combat assignment. Advanced training in formation flying, instrument flying, gunnery, and combat tactics added another 100 hours. Japanese pilot training had collapsed. Fuel shortages limited training flights to essential minimums. New pilots entered combat with 50 hours total flight time, 1/5 the American standard. Veteran pilots who might have trained new pilots were dead, lost in combat that consumed experienced aviators faster than schools could replace them. The captured P-47 at Chofu flew 2 more test flights before fuel supplies were exhausted. The second flight, conducted May 9th by Lieutenant Saburo Sakai, Japan's leading surviving ace with 64 confirmed victories, reinforced Kudo's assessment. Sakai's report, archived at Japan's National Institute for Defense Studies, states simply, "This aircraft cannot be defeated by Japanese fighters in competently piloted hands. Our survival against P-47 seconds depends on American pilot error, not Japanese skill." The third and final test flight occurred May 14th. Captain Kudo flew again, this time testing maximum performance at low altitude. He achieved 453 miles per hour at 5,000 feet, approximately 100 miles per hour faster than any Japanese fighter could manage at the same altitude. After landing, ground crew inspected the R-2800 and declared it still in excellent condition despite running on inadequate fuel. American engines tolerated abuse that would destroy Japanese power plants. The technical arsenal attempted to preserve the captured P-47 for further study, but events overtook plans. On May 25th, B-29 bombers attacked Chofu Airfield during a daylight raid. Incendiary bombs destroyed hangars, burned aircraft, and killed 63 personnel. The P-47 survived the raid, but was damaged by bomb fragments. Efforts to repair it ended in June when Japan's situation became hopeless. The aircraft was deliberately destroyed in late July to prevent recapture. Captain Kudo survived the war. In post-war interviews, he consistently emphasized the industrial gap rather than pilot skill as the decisive factor in air combat. His 1952 interview with American aviation historians includes this assessment. Japanese pilots were brave and skilled. American pilots were brave and skilled. The difference was American pilots flew aircraft with 2,800 horsepower, while we flew aircraft with 1,000 horsepower. Courage doesn't overcome that advantage. The P-47 Thunderbolt served throughout the Pacific War with devastating effectiveness. 5th Air Force units flying P-47 seconds achieved kill ratios exceeding 10-1 against Japanese fighters. These ratios reflected not just pilot skill but overwhelming equipment superiority. American fighters could choose when to fight, where to fight, and how to fight. Japanese fighters could only react and hope for mistakes. Production statistics tell the final story. Total P-47 production, 15,683 aircraft. Total Japanese fighter production, all types, entire war, approximately 30,000 aircraft. America built half as many Thunderbolts alone as Japan built fighters of all designs, and the Thunderbolt was just one of several American fighter types produced in comparable numbers. The R-2800 engine became the most produced aircraft engine in American history. Total production, 125,000 engines. These engines powered not just P-47 seconds but also F-4U Corsairs, P-61 Black Widows, A-26 Invaders, and dozens of other aircraft types. The single-engine design that Captain Kudo flew at Chofu became the power plant for an entire generation of American combat aircraft. Japanese engineers studied the captured R-2800 extensively. Technical drawings were created, components were measured and analyzed. Metallurgical tests examined material properties. The conclusion was unanimous. The conclusion was unanimous. Japan, the precision machining, specialized materials, and quality control systems required were beyond Japanese capability in 1945. This realization informed Japanese post-war aviation development. When Japan rebuilt its aircraft industry after the war, engineers focused on licensed production of American engines rather than developing indigenous designs. The knowledge that American aviation technology had surpassed Japanese capabilities by such wide margins influenced decades of subsequent industrial policy. The P-47 itself became legendary in American military aviation. Post-war analysis showed Thunderbolts destroyed 1,100 enemy aircraft in air-to-air combat while losing only 766 P-47 seconds to all causes, including ground fire, accidents, and mechanical failures. Air-to-air exchange ratio, approximately 4.6-1 in favor of the P-47. More impressively, P-47 seconds flew 546,000 combat sorties during the war, more than any other American fighter type. Total combat hours exceeded 1.9 million, bombs dropped, 132,000 tons, rockets fired, 60,000, ground targets destroyed, approximately 9,000 locomotives, 6,000 tanks and other armored vehicles, and 68,000 trucks. The Thunderbolt proved equally effective as a ground attack aircraft and air superiority fighter, versatility that reflected its robust design. The heavy airframe that made it sluggish in dogfights made it durable in ground attack missions, where anti-aircraft fire was intense. Pilots learned they could trust the P-47 to absorb damage and bring them home. That trust translated to aggressive tactics that multiplied combat effectiveness. Republic Aviation continued developing the Thunderbolt through war's end. The P-47 Newton's model, introduced in late 1944, featured increased fuel capacity and improved range, addressing the aircraft's only significant weakness, Maximum range increased from 800 miles to 2,300 miles with external tanks, allowing P-47 seconds to escort B-29 seconds on very long-range missions to Japan. Captain Kudo's May 1945 report circulated through Japanese military and government circles as evidence of the hopelessness of continuing the war. Combined with similar reports on B-29 bomber capabilities, American submarine technology, and radar systems, the accumulated intelligence painted a picture of overwhelming American technical and industrial superiority. The atomic bombings of Hiroshima and Nagasaki in August confirmed what aviation intelligence had already revealed. America possessed weapons Japan couldn't match, and industrial capacity Japan couldn't challenge. The decision to surrender stemmed partly from recognition that conventional resistance was militarily futile. Kudo's test flight report contributed to that recognition by documenting exactly how far Japan had fallen behind in aviation technology. Today, only one Republic P-47 Thunderbolt remains in flying condition in Japan, operated by the Commemorative Air Force as a memorial to aviation history. The aircraft serves as a reminder of the industrial and technical gap that defined the Pacific War's outcome. The lessons from Kudo's evaluation remain relevant. Wars are won by industrial capability as much as battlefield courage. Producing adequate equipment in sufficient quantities matters more than achieving theoretical perfection in limited numbers. The P-47 wasn't the most maneuverable fighter, or the longest ranged or the most heavily armed. But it was fast enough, powerful enough, and durable enough to defeat every aircraft it encountered. More importantly, America built it in numbers that made victory inevitable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.